So let me recall what we did in the last lecture. In the last lecture, we saw many results related to basis and dimension. Basis and dimension of a vector space. So at the end, we proved a result that if we have a vector space and we have a subspace of it, then we can always find another subspace. Let's say W. The given subspace is U. Then we can find another subspace W such that V can be written as a direct sum of U and W. Moreover, in addition to that, if the vector space is of finite dimension, then we can say that the dimension of V is equal to dimension of U plus dimension of W. All right. So just let me disconnect my pencil. So there's some issue. All right. Okay, so let me know if you can see my screen or not.
No, sir.
No, sir.
Can you see it now?
No, sir. Yes, sir.
Yes, sir.
Yeah,
Yes.
now.
Okay, fine. So today is lecture 8. Today is 2nd September. By the way, let me first ask you that did you receive my email regarding the grade scope login and the examination details?
Yes, sir. Yes, sir.
Yes,
Okay,
sir.
so all of you, so did you try to log into grade scope?
Yes, sir.
Yes, sir.
So
Yes, sir.
and you can see the course, right? MTL
Yes,
50
sir.
Yes,
is
sir.
there.
Yeah,
Okay.
MPL 504 is there.
Yeah. So I have prepared a kind of mock examination there. It is like a trial examination or demo examination, and then in that the exam will open today at 11 and then it will close tomorrow at 3 p.m. So in the meanwhile, you can open it, you can download the question paper from there, and then you can like work out something, and then you can upload your responses to that there itself. So it's like we won't collect. I will not provide you the question paper via email. You will have to download it from there during the exam or whenever the actual exam happens. And also, I will not collect anything on my email ID. So you will have to upload your responses there itself. Okay, so we will correct the question paper, the answer scripts there itself, and you will also be allowed to see and apply for regrade if there is anything there itself. So everything would be on grade scope. So you please make yourself familiar with the grade scope if you are already not familiar with it. So you try to upload, let's say 4 or 5 pages. You don't have to like work out. Of course, if you can, if you work out all the problems and do it and upload it, it is okay. But I'm not going to correct it. It's just for your practice purpose. You just upload 4 or 5 pages, assign the question number to at least first and second, so that the mapping is there, and then you just make yourself familiar with it. So whenever the actual exam happens, then you don't have any technical issue with this grade score. And if there is anything, any problem, you can let me know. Okay. So let us start today's lecture. So we have already seen one result in the last class at the end. Let me prove a similar result. Let me start today's lecture with a similar result. So what it says that if suppose we have a vector space, let's say. So let V be a vector space of finite dimension. So V is a finite dimension vector space over some field M. Okay. And assume that U1 and U2, they are subspaces of V, subspaces, right? Then, then the dimension of u1 plus u2 is equal to dimension of u1 plus dimension of u2 minus dimension of u1 intersection. So basically, you know that if u1 and u2 are subspaces, then their sum is again a subspace that we have seen, and also the intersection is again a subspace. Intersection of two subspaces is again a subspace. In fact, you can take a intersection of any collection of subspaces, and that would again be a subspace. Okay, so that you can verify. So let us prove this. The proof is not difficult. The proof is very easy. But I want to convey one idea here in such a question, how to start the proof. So can you tell me, I mean, how to prove this? Just give some idea. If you don't have to remember, you don't recall whatever you have done in the past. You try to think newly, like we have such a question. What we are given just a vector space and two subspaces, and we have to prove this. Then how to start?
So we can
Can you?
modify it.
So firstly, let dimension of u1 is equal to n and dimension of u2 equal to n, and
Hmm.
then it is a basis of u1, then it is Li subset of v, then this basis can be extended to form a basis of v in
Hmm.
this way, we forward.
But yeah, so let me write. So he's saying the following. Let me write this side. Your idea. So you are saying that assume that m is the dimension of, let's say, u1, and let's say uh, k be the dimension of u2, and then you are saying that you extend the basis u1. So let's say b1 is a basis for this, b2 is a basis for this. So you extend b1 to, let's say, some b1 tilde basis of v. This is what you are saying. And then you are saying that b extend b2 also to a basis b2 tilde of v. Then what?
Sir,
Yeah.
sir means we can, as you have taken, one of my friend has given the m and k as a dimension of v u1 and u2. Now, sir, we
Hmm.
can look for, we can extend dimension of u1 up to the dimension of u1. Sorry, a dimension of u1 plus u2 vector space.
So you want to say that instead of v, you want to extend it to u1 plus u2. This is what you are saying?
Yes,
Yeah.
sir.
So let's say
Yes, sir.
u1 plus u2. Okay, so I will modify then something because you are suggesting. So let's say it's instead of v, it's u1 plus u2, and this also u1 plus u2. Okay. Then what?
No, sir. Any one of them. Any
So
one of
any
them.
one of
Not,
them. Okay. Okay. Let's say this one then.
sir. That means it will imply that dimension of whatever the extra linearly independent set we are going to add in B1 to get B1 tilde for U1 plus U2 for vector space U1 plus U2.
Hmm.
That will be represent dimension of U1 plus U2.
That's fine. Okay. So you have to add extra vector here, of course. If
Yes, sir.
b1 is the basis of this, then you have to add extra vector to make it b1 tilde, basis of b1 u1 plus u2. This is fine. Then what? What would be
And
these extra vector? How would you say that these extra vector have some?
sir
Sir,
means, sir,
Yes.
as the vectors are coming as the vectors are coming from U2, which is not there in U1.
Hmm.
Yes, sir. And it will imply
So
that,
that you don't know. That you don't know. They can be of the form u1 plus u2 also.
yes, sir.
It's not like all the vectors are coming. You may not have the added vector of the form 0 plus u2, where u2 is in u2. They may be of the form u1 plus u2.
so so we can let M is the dimension of U1 intersection U2. and then we can extend u1 intersection u2 to u1 and u2.
Okay,
And
both.
let's
Yeah.
say let's say dimension of u1 is now p and dimension of u2 is q.
Hmm.
And then writing the basis for these in arbitrary terms
Mhm.
and taking their sum, we get dimension of u1 plus u2. And this is how we're going to prove this.
Yeah, so this is basically the idea. So what I wanted to say here, so that let's see, whatever like idea you gave first initially. For example, here take the dimension basis of u1 and u2 and extend it to v or u1 plus u2. That may not give you. I mean, that will not give you something for like clearly for u1 intersection u2. So whenever you have like this kind of situation where you are given some subspaces, especially in finite dimension, when you are given some subspaces, then what you do, you always start with the smallest subspace and then try to extend its basis to the bigger one, and that way that will give you something definitely. For example, here we have four subspaces u1 u2 u1 intersection u2 and u1 plus u2. So what I will do, what is the smallest subspace in this
Intersection.
intersection? So
Intersection.
let us start with the intersection, with the basis of intersection. Now it is in the intersection, so it will be a subspace of u1 as well as a subspace of u2. So then extend this basis to a basis of u1 as well as a basis of u2. Now this way you may get some idea to how to prove this. So for example, let me just write. When I will write, you yourself will give me like some idea to how to prove this. So let me just write whatever I said in the mathematical language, and then you yourself will get some idea. Okay, so let us prove this. So let's say we know that u1 and u2 are subspaces. So u1 intersection u2, this is also subspace. Now since v is finite dimension, so this would also be finite dimension. So let's say v1 to vk, this is a basis of u1 intersection u2. Okay, now what I will do, since it's a basis of u1 intersection u2, I will extend it to a basis of u1 and also a basis of u2. So let's say v1 to vk, these vectors are from u1 intersection u2, and I will add some vectors, let's say u1 to ur, let's say, then this becomes a basis of u1 to ur. This becomes a basis, let's say, basis of u1. So I have extended this to a basis of u1, and similarly I will add some vectors, let's say w1 to wp, so that this becomes a basis of u2, right? Now what would be my claim here? Now this is what we have done, I mean we have discussed so far. Now I want to prove that dimension of u1 plus u2 is equal to this thing. Now what is enough from this information? Can you give me some idea so that I can say that okay, this claim can be proven?
So now we can write the basis of dimension u1 plus u2 also from this information.
What would be that?
That will be v1 to bk, then u1 to ur, then w1 to wp.
So this you are saying that this will become a basis. No, you have to check whether this become a basis or not. But
This
if this
is
becomes
this is we are claiming right now. Then we
this
will
right,
prove this. Then we
right,
will prove this.
right. So your claim, so we claim that, so I'll just write what you said. So we claim that this new set, which is the collection of vectors vi's, vectors ui's, and vectors wi's, this form, let me call this set as b. So this form a basis of u1 plus u2.
Yes, sir.
Now why, yeah, so why this is enough? Because so we have not done this, but we have to prove that this is this is a basis. Because if so, if this is the case, if so, then what we get, then dimension, you see, dimension of u1 plus u2 would be what? it would be K plus R plus P. But then I can write this as K plus R, K plus P minus K. Now you see here, what is K plus R? This is a this is a dimension of U1.
U1.
This is dimension of U2, and this is dimension of U1 intersection U2. So we are done. So we are done if we show that this set B is a basis for U1 plus U2. So let's try to see this. Now we have to prove that this is a basis. So we need to check two things. First is that this spans the whole space. This set B spans U1 plus U2, and this is also linearly independent. Okay. So first thing to check with that U1 plus U2. So U1 plus U2. So the first claim is U1 plus U2 is equal to span of this set V1 to VK, U1 to UR, and W1 to WP. Now, can you show that this is true? I'm saying that this is very easy to check.
Yes, sir.
Yes, because yeah.
Sir, span of W1 span of U1 plus U2 equals to span of W1 union U1 union
U1 union.
U2.
So
सर इनके बेसिस का भी यूनियन हो जाएगा तो इसलिए वो इसको स्पेन करेगा U1 plus U2.
So here again, here you are given two sets. You want to show that these two are equal. So you are given this one and you are given this one. You want to show these two things are equal. What you have to show, you don't have to jump to any argument. Just try to prove with the basic arguments. So you have to prove
So
that this is a subset of this and this is a subset of this. That's all.
let's
सर
say
इसका
some B
कोई
vector belongs to U1 plus U2.
सर इसके लिए ना कॉम्बिनेशन में लिख देंगे फिर इसको.
Yeah, so this you can easily, so I guess you can prove this. So let me leave this one. So let me complete this as an exercise. So I will leave this thing, and then I will move to proving that the set B is linearly independent. So now to show that this is linearly independent. Okay. So now how to prove that this is linearly independent? We'll just use the definition. So let's say alpha 1 v1 so on up to alpha k vk plus beta 1 u1 plus to so on beta r ur plus the gamma 1 w1 and so on up to gamma p wp is equal to 0. Let's call this equation star. Okay. Now I need to show that all these alphas are 0. In order to say that, so assume that these alpha is, beta is, gamma is, they are scalars. That means they are coming from the field. So this equation is 0. If the set B is linearly independent, then this should imply that all these alphas, betas, and gammas, they should be 0. All should be 0. So now what can I do from here? Any idea?
Alpha 1 V1 dash alpha K VK plus beta 1 U1 dash beta R UR is equals to minus times of remaining.
Okay, so you are saying that you take these gammas to the other side. So let me do that.
Okay.
Alpha 1 so on alpha K VK plus beta 1 U1 and so on beta R UR, and then you are saying that you take these to other side. Gamma P WP. Fine.
Then, sir, we can see that this alpha 1 U1 alpha K beta 1 this belongs to set U1.
So clearly this set belong to, so
U1.
clearly, yeah. So clearly this thing belong to U1. Because these vi's and ui's, they form a basis of u1. And what about this side?
And this is subset of U2.
So this belongs to u2. So this element belongs to u2. So you can
Yes.
see, so what you can say from here?
From here, this is as it is linear. All V1, VK, U1, UR are linearly independent, as we assumed earlier. Therefore, sum of this is zero.
Why?
So,
This from
No, sir,
here we
both are
cannot say
belong to
that.
U1 intersection U2.
Yeah, so from here you can say that these vectors belong to u1 intersection u2, whether you take left hand side or right hand side. So for example, from here what you can say, so this implies that this minus gamma 1 w1 and so on up to minus gamma p wp, this belong to u1 intersection u2. This much you can say. But since this belongs to u1 intersection u2, then what? Then what does it mean?
Then
then we can
we
write
write
it
a
equals
general
to the
element of
U1 intersection U2
Yes.
element.
Yeah, so this belongs to u1 intersection u2. So you write this vector as a linear combination of the basis vectors of u1 intersection u2. So these basis vectors are vi's. So what I'm saying is that you write this vector because this belongs to u1 intersection u2. So we can always write this as a linear combination of basis vectors of v1 intersection u2, which are vi's. So this is for some
Yes.
ci's in f.
Yes.
Right? But then this implies that minus gamma 1 w1 and so on up to minus gamma p wp minus c1 v1 and so on up to minus ck vk equal to 0. But what does it mean?
This gives U2 is a linearly independent set.
Since u2 is linearly independent, so this implies that gamma
All
i's are
gammas are
0. Yes,
CI.
for all. Yeah, for all I equal to 1 to p, all gamma i's are 0. Similarly, ci's are also 0. But since we know that gamma i's are 0 for all I equal to I from 1 to p, so I will put substitute this in equation star. So therefore, from star, what we can say from equation star, what we can say,
All all beta are zero.
all alpha i's and beta i's are 0 because
Yes.
gamma i's are 0. And
Yes.
then if this expression is 0 here, then we are left with only this, but we know that vi's and ui's, they form a basis for u1 and therefore they are linearly independent. So if this is equal to 0, then all these alpha i's and beta i's should be 0. So therefore from star we can say that alpha i's are 0 for all I equal to 1 to k. Similarly beta i's are 0 for all I equal to 1 to r. And therefore this implies that beta is a, or beta
This
form a basis of u1 plus u2. This set B form a basis of u1 plus u2. And we are done. Okay. So now what is important here? The proof is very easy. Proof is not that difficult. But the important thing is to how to start. So once you get the start, so let's see here. The main thing here was to start from a basis of u1 intersection u2. Once you have that, then things were very easy. Then they just follow. So it's important before you start, just read the question carefully and then see what should be done, how you can start the proof. So this is when we
Sir,
have two vector space. Yes,
sir, I have a doubt, sir. Please show the second page.
this one.
S- Uh, yes, sir. Sir, here you have wrote it that minus R1 W1 data dash minus gamma P WP belongs to U1 intersection U2. Sir, how?
Right.
Because sir, it is belong to U2 only. So there is a possibility that it will belong only U2, not U1.
No, but you look at this expression na, here.
equals to
Left side.
that
So
belongs to U1.
one side belongs to u1,
Yes,
the
sir.
other side belongs to
Yes,
u2.
sir.
That means what? Either they both belong to u1 and both belong to u2. They both belong to U1 and both belong to U2. So what does it mean? It means they belong to the intersection,
Yes, sir. Linear combination. Yes, sir.
right?
Yes, sir.
Okay. So so this is for when we have two subspaces. But can you extend this result? So this is what comes to our mind next, right? So we have this result for two. Then like can we, or let's say let me write it in this way. Can we prove or disprove? So prove or disprove the following, that if we have a vector space, again finite dimension, the same way, and we have, let's say instead of one we have three, instead of two we have three subspaces, let's say now u1 u2 or u3, these are subspaces. Then the question is, can we extend this result? So what would be the extension of this? Can you tell me? Dimension of u1 plus u2 plus u3, how should I write
Equals
this?
dimension of U1 plus dimension of U2 plus dimension of U3 minus dimension of U1 intersection U2 minus dimension U2 intersection U3 minus dimension of U1 intersection U3 plus dimension of U1 intersection U2 intersection U3
Yes, sir.
plus, that's it, sir.
So is it correct? I mean, is it prove or disprove? What is your guess?
True, sir. True,
Disprove.
sir.
Disprove.
It is true. So,
Yes,
and
sir.
you can prove
No
it
true, sir.
similarly.
Yes, sir.
Yes.
Okay,
Let
so
U1 intersection U2 intersection
yeah,
U3.
just a minute, because before you start proving, somebody said that it is not true. So if he gives you one example, then whatever proof you are giving, that is not going to be like going to work. There is some problem. So some of you said that it is not true. So can you just give me an example? If you're saying that it is disprove, then you can disprove it by giving a counter example, right? So an example of a vector space and three subspaces, that doesn't follow, this doesn't satisfy this.
Yes, sir.
Yeah.
So we
So
take
you
V
are,
equal to R square.
let me write this. So you are saying that this is disprove.
Yes, sir.
Let me just write it, just a minute. Huh? So this is just for your notes, so that you can look at your notes again. So you are saying that it is disprove, and you are disproving it by an example. So what is your example?
So V
You are
equal to
taking
R
V as
square.
R2,
Yes,
okay,
sir.
and
And
U1 is,
U1 is equal to X comma 0 and
so
X
it's
belongs to
X
R.
comma 0, X belong to R, okay.
And
U2,
U2 equal to 0 comma Y belongs to R.
Y belong to R, fine.
And U3 equal to suppose X comma X.
So just to avoid confusion, because in the last in tutorial you had
Z
some
comma Z, Z
confusions.
comma Z.
So let me write this Z comma Z.
Yes, sir. Then from here dimension of U1 equal to 1
Mm-hmm.
and dimension of U2 equal to 1 and dimension of U3 equal to 1.
Right.
Now
Then
U1 intersection U2 equal to 0.
similarly for others also.
Yes, sir. Then dimension of
Others.
all three is equal to 0.
Right. All four.
And if you take U1 plus U2 plus U3 equal to R square.
Yes. So U1 plus U2 plus U3, it is equal to R square.
Then dimension of
So,
U1 plus U2 plus U3 equal to 2. But
mhm.
from right side it gets 3. Then 2 equal to 3, which is not true.
Right. Exactly. So this is correct. So he's saying that since this implies that dimension of U1 plus U2 plus U3, which is equal to 2, but which is not equal to dimension of U1 plus dimension of U2, the other thing. So this right side expression here. Sorry, this expression here. So the right side gives you uh,
3.
3. So now you can see that this is not true. You cannot extend, you cannot like generalize this result. All right, so there are some other simple results which you can which you can try, or which you can learn or read in the in the textbook. Mostly I'm following Hoffman and Kuhn, but there are some other results taken from other textbooks also. But these are some standard results which you can find anywhere.
Sir,
You should work out some other problems also. Let me finish. I will also upload a tutorial sheet today, a new problem sheet kind of thing, where I will include some more problems related to vector space, subspace, and this dimension, basis and dimension. So with this, we can start the next topic. I mean, of course, we will be using whatever we are learning, but let me first like introduce some of the basic things. The next topic is linear transformation. Yes.
सर इसमें ऊपर वाला
Yes.
रिजल्ट अप्लाई कर सकते हैं ना?
Which one?
इसमें जैसे U1 को एक सब स्पेस मान लें और U2 प्लस U3 को एक सब स्पेस मान लें, तो फिर ऊपर वाला रिजल्ट अप्लाई हो जाएगा?
So what you are saying, this is prove or disprove?
नहीं, ये तो होगा, डिस्प्रूव होगा, लेकिन जैसे U1 इज इक्वल टू W1 मान लें और U2 प्लस U3 इज इक्वल टू W2 मान लें, फिर ऊपर वाला रिजल्ट अप्लाई कर सकते हैं ना?
So, yeah, so the upper wala result is true for any two subspaces. So U1 is a subspace, U2 plus U3 is a subspace. So then again you can do it. Of course you can do that.
ओके सर.
You can do that. I mean, whenever, so we don't have any, we did not have any assumption in proving that result. We just had one vector space V and two subspaces. That's all. Okay, so let us start linear transformation. So let me first define and fix some terminology, and then we'll see some example. So can you tell me, I mean, what you have learned so far, and just give some definition of a linear transformation?
Yes, sir.
Precise definition. Yeah.
A mapping from a vector space to another vector space over the same field is called a linear transformation if TV1 plus V2 equal to TV1 plus TV2, where V1, V2 belongs to, if we have a linear transformation T VF equals to WF, then V1, V2 belongs to V, and second property is T alpha V equal to alpha T V, where alpha belongs to F and V belongs to V, vector space.
Right. Then such a
And
function is
field
called.
and field same field and field should be
Yes, yes.
Yes, sir.
U and P.
Okay, fine. So let me write. So this is correct. So what is a linear transformation? So let we suppose that we have two vector space V and W over the same field F, and then a linear transformation, a linear transformation from vector space V to W is a function. This is just a function with the following two properties. So what is the first one? It is, let's say, let me write it a T. So a linear transformation T is from V to W is a function T with the following property that T U plus V is equal to U plus TV for all UV belongs to V, and the second is T of alpha U is equal to alpha times TU for all alpha belongs to F and U belongs to V. So if a function from V to W satisfy these two properties, and we call that function as a linear transformation. Linear transformation from the vector space V to a vector space W. Now these two properties, you can combine them and you can write instead of one property, instead of two, or equivalently, if the function satisfy the following property, which is alpha u plus v, and it would be alpha tu plus t of v. You can verify that both these here and here, these two things are equivalent. Right? So if you have to check that whether a given function is a linear transformation or not, you just check these properties and then you're done. Now let me fix some terminology. So for example, we know that if V is a set, W is a set, then we can define many functions. And if these functions satisfy these properties, then we can collect all these linear transformation and put them in one set. So we are fixing a notation for that set. So let us denote the collection of all linear transformation from vector space V to W by this. So this is the collection of all linear transformation from V to W. Okay, so P is linear transformation. Okay, so for linear transformation, I may use this abbreviation L dot T dot. Okay, a linear transformation from the vector space V to V. So in the case when W is equal to V, is called a linear operator. Okay. Similarly, a linear transformation from a vector space V to F. So F is also a vector space, right? The field over itself is also a vector space. So a linear transformation from V to F is called a linear functional. Okay, all right. So these are the basic terminology we'll follow in this topic, linear transformation. But there are some simple observation you can say. So let me write this also. So if suppose we have a, let's say T is a linear transformation, let's say from V to W. So now if I write T belongs to L of V comma W, that means T is a linear transformation from V to W. Then what would be T of 0?
0.
Why?
0.
Sir,
Zero
opposite
of
में
W.
नहीं है.
Zero vector of W.
0 vector of W. So you are saying that
0
then in
vector
this
map
case
0.
0 vectors map 0 because of this property. But why this is true?
Sir, homomorphism है T.
What is homomorphism?
Sir, TU plus V is equal to TU plus TV है ना.
Hmm.
तो homomorphism
Sir,
में
we
property
can
होती है
prove
ना.
it by
T of 0
या
plus
फिर 0
0
plus 0 ले ले.
Yeah. So
So we
why
can apply
to
the
use
second
this?
property of linear transformation which you given.
So it is property of field and vector space where 0 dot x equal to 0 for all x belong to V.
Mhm.
Then
Yeah. So there
T
are,
of 0
yes.
dot u equal
0
to 0 dot T of u, and T of u is element of V, and alpha is element of a field. Then 0 dot x equal to 0 for all x belong to V. Hence proved.
Okay.
सर अगर t 0 इक्वल नॉट इक्वल्स टू
T
0
of
लेंगे तो इस प्रॉपर्टी को सेटिस्फाई.
Hmm. So
So
basically,
we can take 0 and 0 in V, then 0 plus 0 equals to 0. Then linear transformation property apply करके prove कर सकते हैं.
yeah. So there are many ways, right? I agree. I agree. There are many ways, and very easily you can prove this. So one way is that you know that if you take 0 in V, then you can write it as 0 equal to 0 plus 0, right? So basically what you are saying is that T of 0 plus 0, which is equal to T of 0, again from the left hand side you can say T of 0 plus T of 0, because T is linear. Now from these two things, because T of 0 is a vector in W, right? So and W is a vector space, so it has an additive identity. You can add the minus of negative identity, additive identity both sides, and what it would be T of 0 equal to 0. There are many ways to prove this. This is one way. You said that you can use the second property also. That is also fine. You can use some other argument, as long as you just use the properties of a vector space and a linear transformation. It is fine. And so there are several examples one can give. I will give examples in the tutorial sheet, but let me just give some basic examples. Say basic examples. For example, we have a zero map. Zero map is what? If suppose we have a vector space V, and suppose that we have a vector space V and W, then zero map is a function from V to W. It's that sends every vector in V to a 0 of W. Then you can verify that. This 0 belongs to this. So it's a linear transformation from V to W. Similarly, you can define identity map. Identity map, it's like a, you can
Linear
denote it by
operator.
I. It's the linear operator. You can take any vector space V and then send a vector V, any vector V to itself. And you can check that this is a linear operator. By the way, when, so I may use this notation also, I forgot to mention. So when W is equal to V, then instead of writing V comma V, I may just write L of V. Okay. So here is this notation. So this is the collection of all linear operators, L of V, instead of L of V comma W. Okay. So this I is a linear operator. All right. Similarly, you can talk about this derivative map. What is derivative map? So if suppose you have a function, let's say from the space of all polynomials over F to all polynomials over F. And what it does, it takes a polynomial here and send it to its derivative. Now this you can verify that this is D is also a linear operator over this set P over F. Similarly, you can, so I am not proving this, but you can check this, you can verify that this is easily a linear transformation. Similarly, you can also prove that integral map. What is integral map? So let's say if you have say, T from the space of polynomials to F, so how it is defined? So you just so let's say R T over R to R, just to simplify it, and then send every polynomial to this integral P of x dx. Now you can verify that this T is a linear functional. T is a linear functional. That means it belongs to P of R2. So these are some map. So why I'm saying, why I have introduced them here, because I may use these terms in the following lectures. The other examples you can find in a textbook, or I will put some examples in the tutorial sheet also. So whenever we have a linear transformation from a vector space to another vector space, we can always associate two subspaces to it. So there are two natural subspaces that are associated with a linear transformation. So what are these subspaces? Can you tell me what are these subspaces?
Sorry, sir, can you repeat? What?
So what I'm saying is that two natural subspaces are
Range
associated,
space and null space.
right, associated with a linear transformation T from V to W. What are these?
Yes, sir, he is
It
correct.
is, yeah,
Null
it's
space
null
and range
space,
space.
Null space and range space.
right? So null space, we will write null of T. In some books, it is also written as kernel of T. Both are the same thing. We'll use null of T. So null space is what? Null space is the collection of all vectors in V such that T of V is equal to 0, right? And similarly, we have range space, or sometimes it is also known as image space. So what is this? It is we will denote this notation. We will use this notation for range space of T. And what it is? It is the collection of all vectors W in W such that they have a pre-image in V. So that means there exists V in V such that T of V is equal to W. Or in other words, the same thing you can write in this way also, that T of V, V belong to the same thing. Now clearly you can check that kernel of T is always a subset of the domain, that means V, and range space is a subset of the codomain W.
Yes,
Okay.
sir.
So for example,
Precisely subspace.
yeah, so we will see whether they are subspace or not. In fact, they are subspaces, you are right. But before that, let me give you this example and you tell me what is the kernel and range of, what is the null and range of this linear transformation. So take this linear operator, let's say D, the derivative operator, from P4R to P4. That means it's the space of all polynomials of degree less than equal to 4 to the same space. And how it is defined? You take any polynomial here and send it to its derivative. Now, can you tell me what is the null space?
Constant
Our
polynomial.
constant function.
Constant polynomial.
Constant polynomial.
So yeah, so
Constant.
I'll just, yes, I agree. It is constant polynomials, but I will write it. Still, I will write it properly just to give you an idea how to find null space and range space. I mean, when you write it properly, it may give you some idea to find this. For example, here by definition, it is collection of all polynomials in P for R, such that
D of
T,
px equals to 0.
yes, D of Px equal to 0, right? Now here again, if I simplify it, then by definition it is the collection of all polynomials such that what is D of Px? It is P dash x equal to 0. Now the derivative is 0, that means it should be
P of
constant
x
polynomial.
equals to constant.
Yes. Space of all constant polynomials. Similarly, if you look at the range of D, then by definition it is collection of all Qx, all polynomials Qx, let's say, such that d of p, there exists Px such that d of Px equal to Qx, or I can write directly that P dash x equal to Q of x for some Px in P for R, right? So what is this? Can you tell me now?
Now T3. T3.
Collection of
Yeah,
all polynomials which degree
Degree.
up to 3.
T3,
degree
sir.
up to 3. So it is P3R. So what would be this Px? This Px would be just the integral of Qx, right? Anyway, so this way you can find null space and range space of a linear operator. This is just an easy example I gave, but you can try with, let's say, some more involved examples. I'll give some problems in the tutorial sheet. But now, as you said that you can check not only null space is a subset of V, it is actually a subspace of V. Similarly, range space is a subspace of W. So let me write this as this as an observation or as a result. Let me write this as a result. That if we have a linear transformation from V to W, then null space of T is a subspace of T. Similarly, range space of T is a subspace of W. Now, these two properties you can prove easily. So I leave them as an exercise for you. So let me give them as an exercise. So you can verify that null space of T is a subspace, and similarly range space of T is a subspace of W. Not only that, you can prove some more properties. You can say that T is 1 1 if and only if. So this notation I double F, this means if and only if. T is 1 1 1 if and only if null
Null
of
space
T
equals to 0.
is equal to
0.
0. Now can you prove this one?
Yes, sir.
Yes.
Yes, sir.
Yes, sir.
So you have what you have to prove. So assume that, let's say, so this is if and only if. So let us prove the if direction first. Suppose that T is 1 1. Then what?
Then there exist two vectors
Okay.
v1, v2 such that t of v1 equals to t of
Yes.
This is fine. No, what I'm saying that you assume that T is 1 1 and then you show that null of T is equal to 0.
Since
Then we
T is
take a
1
element
1,
x belong to NT, and x belong to NT, then tx of 0, and 0 equal to t0, then tx equal to t0, और from 1 1 it is x equal to 0. Then
Yes.
ये इससे प्रूफ हो गया कि जो हमने एलिमेंट लिया था वो 0 ही होगा, hence NT equal to
0.
0.
Right, v equal to 0. So this implies that every vector. So what does it mean? It means that whatever you just explained, it means that null of T is a subset of 0. This is what it proves. But the other way is also true, because 0 null space 0 is always there. T of 0 is equal to 0, so 0 is always there. So this is also true, and therefore null of T is equal to 0. This is fine. So you can verify this. What about the other direction? If null of T is equal to 0 space, then can you show that T is 1 1?
Yes, sir. You take
Yes,
tx1
sir.
equal to tx2, then t of x1 minus t of x2 equal to 0. Then by first property, t of x1 minus x2 equal to 0. Whenever tx equal to 0, then x belongs to NT. Means that x1 minus x2 belong to NT. But we have NT equal to 0 element only. Then x1 minus x2 equal to 0. Hence x1 equal to x2.
Right. So this way also you can prove. So yeah, this you can prove. This is easy, so you can prove it. So let me write the next one. Similarly, you can show that T is onto if and only if range space of T is equal to W. Can you prove this also? So T is onto if and only if range space of T is equal to W. Can you prove this? Can you prove this one also?
Yes, sir, we can try.
Yeah, so let us try. Yes, that should be the attitude. Let us try. So let us prove the if direction first. Suppose that T is onto, then what you have to show? You have to show that. So we have to show,
Range space
always
equals to
write,
W.
always. So whenever so if you don't have any idea, you try to start and write what you want. So you are given T is onto, and you have to show that range of T is equal to W. Now, one thing is clear. So we have to show both side equality. So one thing is clear. We know that range space of T is a subset of W, right? So clearly this side inclusion is straightforward, right? We just have to show the other way. Yeah, so then for the other way, what you have to do?
We have T is onto, then every element of W is the मतलब उस हर एलिमेंट W के हर एलिमेंट के लिए एक V मिलेगा जो T of V इक्वल्स टू W होगा, सो वो रेंज बन जाएगा.
Right. So, but how to write this? So, in order to prove that W is a subset of, so what we have proved? We have proved that range of T is subset of W. Now, next we
sir.
have to show that W is a subset of range of T. In order to do that, whatever you
We
said,
have
that
to
idea will be used. Yeah, you just take a vector, let's say W in W.
W in W.
Right.
Then we
W in
are
W.
able to get a V in V.
Because T is onto.
Yes, sir.
So there exists V in V such
In V.
that T of V is
T of
equal to
V
W.
equals to W.
But then this implies that W is in the range
Range
of T.
space.
Right.
That's
And similarly, you can prove the other direction also. So if suppose range of T is equal to W, then actually T is onto. This is very straightforward, right? By definition, this is
sir.
straightforward. So these observations you can see. Now, whenever, let me fix this also. So whenever null space of T, I don't know whether the vector space itself is finite dimension or no, but whenever, so let me fix this. Whenever null space of T is of finite dimension, then we define nullity of T as the dimension of null of T. Okay, sorry. So I'm using so null of T. And similarly, if range of T is finite dimensional, is of finite dimension, then we say rank of T as the, we define rank of T as the dimension of range of T. All right. So this is just some terminology will follow whenever I say that nullity, that means the dimension of the null space, and the rank is the dimension of. Okay, so using this, you can prove one of the important result, one of the most important result for this finite dimension, this linear transformation or finite dimension vector spaces. So what it says the following, that says the following. So let me just write this result. This has a name. It is called rank
Rank
nullity
nullity
theorem.
theorem.
Yeah. So what it says, can you recall?
Rank of T plus nullity of T equals to dimension of V.
No, you have to say the complete statement. So whenever you are
V
saying
is
something,
finite
just say it complete.
dimensional.
Start with a vector
Self
space.
theorem.
If we can W be two vector spaces, then
Mhm.
T maps from V to W be linear with V is finite dimensional. Then nullity plus rank T is equal to dimension of V.
So only V should be finite dimension. This is what you are saying.
Yes, sir.
Yes, sir.
So yes. So let V be a finite dimensional vector space and T be a linear operator from V to W. W is another space. Okay. Then you can show that range of T. So see, V is finite dimension, so all its subspaces are also finite dimension. So that means null space would always be finite dimension. But range of T is a subset of W. It's a subspace of W. So and W, we don't know whether it is finite dimension or not. So range of T, that means that is a subspace, that also we don't know. We cannot say that it is always finite dimension. But if V is finite dimension, then you can say that range of T is always finite dimension. It is finite dimensional subspace of W. Not only this, and you can prove that dimension of V is equal to nullity of T, that means dimension of null space of T, plus rank of T. All right. Now let us see the proof of this. Okay. Now tell me how to start. We want to prove this one. So what we have to prove first? We have to prove, we can only talk about this statement if we know that the rank is the dimension of range of T, or range of T is finite dimension. So the main aim here is to prove first that time range space of T is finite dimension. What is given? The given is just a finite dimension vector space and T a linear map, linear transformation from V to W. Yeah. Now tell me how to start. Use the same idea what I mentioned
Yes, sir.
at the
In
beginning of
order,
this class. Yeah.
uh,
So see, range of T, we have to prove that it is of
And
finite
firstly, sir,
dimension.
assume that
Yes.
nullity of T is n, yeah, or k,
Mm. Mm.
and then suppose V1, V2, Vk is a basis of null space, then
Mm.
it is extended to form a basis of V, because the null space of T is a basis of subspace of V.
Mm.
Then V1, V2, Vk and U1, U2, Up is a
Mm.
basis of V.
Mm.
And we apply, we actually claiming that um, uh, range T is basis of range T is equal to T of U1, U2, Up,
Mm.
because we have a
Yeah.
theorem that RT equal to span of T beta, of where
Mm.
beta is basis of V.
RT of
then then टी वी वन टी वी टू डॉट टी वी के जो नल स्पेस की हमारी बेसिस थी वो सारी जीरो हो जाएगी, क्योंकि वो नल स्पेस बिलोंग कर रही है.
mm.
तो we have u1 tu1 tu2 and tup, and we claiming that it is basis of range space.
Sir,
Yeah. So yes, yes. So you want to say something? All
sir,
right.
we can say
So
that
yes, yes.
suppose that hello, sir, we can say that suppose that W belongs to range T.
Uh, what is W?
Then corresponding
What is W? This W given subspace?
belongs to range T.
Your voice is not clear.
Hello?
So you're saying that you can start by saying that W belongs to range of T. What do you mean by W? W is this vector space or what?
W is an element.
W is
W
an
is an
element
element of range
of
T.
then.
Range T.
So this is how you want to
Hello?
start this proof.
Yes, sir.
So
I'm not able to
then,
see your.
so
Sir,
then,
what you written, I'm able to see on the screen, sir.
so you cannot see my screen. So how about others? Can you see
Sir,
my
what you
screen?
It's
Yes,
visible, sir.
sir.
It's
It's
visible.
visible.
Very
Okay.
visible.
So we can also prove this. Let us suppose there are dimension of V is n. That means n. There are total n element in the vector V, vector space
Hmm.
V. In n vectors element, some will map to the zero element and some will be mapped to the range of the W.
Hmm.
Hello. Yes, sir.
Yes,
Then,
yes.
sir, let us suppose that m is the number of the element who's going to the nullity. I mean, zero vector space. And let us suppose beta is the number of those vector who is going to map in the vector space W.
Hmm.
and that is all whose mapping to the vector space W is also known as the rank.
No, but
I think.
all the vectors are mapping to vector space W only. Zero is also an element of W.
Yes,
No,
sir.
the thing is that the problem in whatever you are saying is that you are saying some vectors will go to let's say zero and some will go to non-zero vector in W, let's say. But then
Yes.
you don't know which are these some vectors. So is there any other better way to write this? Whatever
Sir,
you are saying. Yes.
sir, I was saying that if W belongs to W is an element of vector space W, capital W, sir, and suppose that
Hmm.
W belongs to range T,
Hmm.
then corresponding to that we are getting an element of vector space V, that is a small v, such that
Hmm.
that is beta V1, such that T
Hmm.
V1 is equal to W.
Right. Then.
And sir, that is then W was an arbitrary element of RT is
Hmm.
range T, and
So.
for if that will, sir, means for every element of range T, we are getting an element of vector space V.
Yeah, that is by
Sir,
definition you will always get. So fine. Then.
yes, sir. Sir, then suppose what means it will implies that the dimension of range T is going to less than equal to dimension of V.
No. Why? How would you say? In this way, you are saying that it is always like range space is always finite.
Sir, no means it. Sir, I'm talking about the range T with corresponding to vector space V. Since the range T is hello,
So from how are you concluding this from here? So
sir,
every vector. Just a minute. Every vector in range of T obviously have a pre-image
yes, sir,
in V. By
yes, sir.
definition, and whatever vector is there in the range space, it will have a pre-image. So that is V. Now you are saying that since V is a finite dimension, so this has to be finite dimension. But this is what we are trying to prove. You are using the same statement, but you have to give a proof for that. You are
Sir,
Okay, sir.
using whatever we have to show.
Okay, sir.
sir,
So
we
yeah.
are given V is finite dimensional. So first of
Hmm.
all, we have a finite basis for V. Then
Hmm.
we take images of those vectors in beta.
Hmm.
Then we will show that T beta will span range space of T.
Hmm.
Uh, then it is a spanning set. So we have a linearly independent subset of that will form
Hmm.
a basis of range space of T. Uh,
Hmm.
so here the rank of T is less than dimension of V, and remaining vectors we will show that that will form null space of T.
What remaining
Then
vector?
सर जो बीटा में थे और
But you have
उससे
not
जो
said
टी
which.
बीटा से हमने जो लेस करे थे.
Yes, yes, I understand what you are saying. The problem here is that you are not taking the correct start. That's what I said. You always have to start in a correct way.
Sir,
So other things just follow.
null
So you are
space of
starting. Yeah, just now
सर
let
नल
us. Yes.
सर नल स्पेस के पहले डायमेंशन एज्यूम कर लेंगे उसके लिए बेसिस
Yeah.
कर
So
लेंगे
what?
क्योंकि
So
नल
as I
स्पेस
mentioned,
वेक्टर
right,
स्पेस
right.
का भी
Yes, yes, I
वेक्टर
understand. So
स्पेस
let me finish. Yeah. So yeah, I understand what you are saying. So as I mentioned earlier at the beginning of the class, that you have to start at the right place. Here, whenever you are giving some subspaces, always choose the smallest one. Now here, you see, you have finite dimension vector space V. So you are starting with a basis of V, and then you are trying to find some vectors which are going to the null space. But that is not like you are not sure which vectors are going. Now, if you start with the basis of null space, then you extend this basis of V, then you know which exactly what are the vectors which are going to 0 and what are the vectors which are not going to 0. And then using the vectors which are not going to 0, you can actually prove that the range space, these vectors, the image of these vectors span the or form a basis for the range space of T. This is very clear. So see here, what we have to do, let us assume that n be the dimension of V, okay, and let's say k be the dimension of null of T. So let's say V1 to Vk, this form a basis of null of T, and some add more vectors, let's say W1 to Wk and minus k, okay, this form a basis of V. This is fine, up to this is fine. Now you know what are the vectors. This Vi is going to 0 and the other vectors, they are not going to 0. So this is clear now. Now from here, this is the information we have. I have not done anything here. I just use the fact that V is finite dimension. Now what we have to prove? We have to prove that range space of T is finite dimension. That means I need to find a basis for this. Now what information I have? So if I want to find a basis for this, I first need to find a subset of this, and that which I can try to show as a basis of this space. Now how to collect vectors for this basis? Now this you can collect by looking at this. So these are vectors in V. If you take the image of these vectors, then they belong to T of V, that means range of T. And then whatever vectors you get, try to use those vectors to show that they form a basis. So for example, here if you take the image of these vectors, then you get 0 for these and non-zero for these. Since 0 you cannot take in your set because it makes your set linearly dependent, so you just take. So what is your claim? Your claim would be to show that T of W1 so on up to T of Wn minus k is a basis of range of T. If you do this, then it proves your result. It proves that range of T is finite dimension, first thing, and it also proves that dimension of V is equal to null of T plus rank of T. So it proves everything if you show that claim, if you prove this claim that T of W1 and so on up to T of Wn minus k is a basis of range of T. Now this you can show by showing that this set spans range of T and it is linearly independent. So this now I give you as an exercise. So show that this is a basis for range of T. Is it okay?
Yes, sir.
Yes. Yes, sir.
So this is very
Yes, sir.
straightforward. So
Yes,
why I
sir.
am emphasizing on the start, because once you start the proof in the right direction, then the other things just follow. So and whenever you are given like some subspaces or some subspaces of a vector space, then try to start by choosing the smallest one. Try to take a basis of that and then expand this basis. That way you may get something. I mean that should be your first try, and then if it doesn't work, then you try something else. All right. So using this result, we can prove several corollaries. Like let me write these as corollary. Corollaries means the results which are just following from this one. So for example, you can prove that if V is a, let's say V and W both are finite dimension vector space. Okay. Then you can show that if dimension of V is greater than dimension of W, then there is no 1-1 map or 1-1 linear transformation from V to W. Do you agree with this? If
Yes,
yes,
sir.
then you have to give a proof idea. So how to prove this?
सर इसके लिए जो अभी थ्योरम प्रूफ करी थी ना डायमेंशन ऑफ वी इक्वल टू डायमेंशन ऑफ डब्ल्यू प्लस डायमेंशन सर डब्ल्यू यहाँ पे रेंज स्पेस है ना.
So range space is a subset of W. Therefore, range space can have at most elements
in the dimension of range space we can have at most elements as equal to dimension of w, and as dimension of w is less than dimension of v, then the difference is some number, and that will be the dimension of null space, and that will be greater than 1, therefore it can never be 1 1.
Greater than 0, you mean
So
greater than 0, it would
Yes,
always be greater than 0, and
yes sir, yes sir.
yes,
सर
so this
ई
is
ओनली
correct.
कैन
Yeah,
सर हम
this is
इसके
correct,
नल
let me
स्पेस
write
को
this. Yeah,
नल स्पेस को नॉन एम्प्टी बता देंगे तो एक हो जाएगा प्रूफ.
yeah, so this is what he said. He said that null space is non-empty because of this result. It follows from this result because dimension of null of t. So since v and w are finite dimension, so you can use the rank nullity theorem. So you can prove that dimension of null of t is always is equal to, by the rank nullity theorem, it is dimension of v minus dimension of range of t. But range of t is a subset of w, so its dimension can be at most equal to dimension of w. So this thing is always greater than dimension of v minus dimension of w, greater than equal to dimension of v minus dimension of w, but dimension of w is strictly less than dimension of v, so this thing is strictly greater than 0. So dimension of null of t is greater than 0 means null of t is not equal to 0 space, and therefore, so similarly you can prove that if dimension of v is less than dimension of w, the same way we can prove this also. Then
Sir, please repeat.
so here, see here, what we have to show, we have to show that there is no 1 1 map. Now if you have any linear map, let's say t is a linear map from v to w, linear transformation, then by rank nullity theorem, dimension of null of t is equal to dimension of v minus dimension of range of t, right? But
Yes,
now
sir.
range of t is a subset of w, it's a subspace of w, so range of t, dimension of range of t is always less than equal to dimension of w, but with a negative sign, the inequality will reverse. So what you can do here is that when you replace dimension of range of t by dimension of w, then this equality would be greater than equal to. Now given that dimension of w is strictly less than dimension of v, so this quantity here is actually strictly greater than 0. This implies that dimension of null of t is greater than 0 means what? Null of t cannot be a 0
Not 1
space.
1. Yes, sir.
Yes, it is not 1 1. That is what we are trying to prove.
Okay, sir.
So then there is, similarly, if dimension of v is less than dimension of w, then there is no onto linear transformation from v to w. And the same way you can prove this also. So let me give this as an exercise. Similarly, the straightforward corollary is the following. It says that if suppose we have a linear transformation from v to w, then this is 1 1, both 1 1 and onto. Can you give me a condition for this? If and only if, or implies at least, let's say one direction. Implies
Dimension v equals
Nullity
to
is
none.
0.
Nullity is 0
Will
and rank equal to dimension of W.
so what you can say from here? Dimension of
Dimension of null space equal to 0.
equal to dimension.
Dimension of v equals to dimension of w.
So
right.
ये तो
This is very straightforward. In fact, the other direction is also true. If we have dimension of v is equal to dimension of w, then you can define a linear transformation T from v to w, which is 1 1 and on 2. But that we will do later. But at least at this point, you can say this much from this above result. Right? Okay. So we are still left with 10 minutes. So let us make this observation. So this observation is very important here. This is a straightforward thing, but let us observe something here. So I'll write this as an observation. Suppose that we have a linear transformation from V to W. So this is a linear transformation. And suppose that we have a basis. We have a basis of V. Okay. Then so let's say this B be a basis V, right? Then we know that if I take any element in V, vector space V, then I can always write V as a linear combination of vectors from the basis elements for some alpha I in F, and these VI's belong to V, right? Just by definition of a basis. So if we have a linear transformation and we have a basis, then whatever vector I take, I can always write it in this way. So this is just by definition of basis. Now if I take the image of T of
Vi
V,
belongs to theta.
Has to be the
oh, Vi belongs to B, sorry. So yeah, you are right. This belongs to B. So then T of V would be what? T of V would be I equal to 1 to n T of summation alpha I Vi, but using the linear property, you can take the T inside sum. So inside the summation, so it would be alpha I T of Vi. Now what you observe from here? You observe that if
T
you
of
know
T of Vi
Can be
generate
expressed as a linear combination of TVI.
so yeah, so the observation here is that if you know what happens on the basis vectors, then only on the basis vectors. So if you just know that what happens on the basis vectors, then you can actually know what happens to every vector on V. So that if your or in other words, if your transformation is defined, you know how it is defined on the basis on the basis elements. That means if you know the what is T of Vi, where Vi's are coming from the basis, then you can tell what is actually the transformation. So the values of T of Vi for I equal to 1 to n, or you say that T of Vi where Vi belongs to the basis, determine the values of T on arbitrary vectors only. So this implies, so what we conclude from here is that, from this observation, is that the values of T of Vi where Vi belongs to B determine, or let's say T of V, let's say Vi is the notation, determine the values of T on arbitrary vectors of V, right? So with this observation, we can state the next result. This result, so let us understand this result in this class, and then we will prove this statement in the next one. So let me write this as a result. So this result is useful to define arbitrary linear maps. Like you can define whatever linear map you want. So you just see what you want from your linear map, and based on that thing, you can define your own linear map. Okay, so this result is useful to define arbitrary linear map. Linear map, sometime I'm using linear map, sometime I'm using linear transformation. So these two things are same. So don't get confused, okay? Linear transformations. How to define arbitrary linear transformation? Arbitrary means depending on what you want from there, you can define your own linear transformation. So let us do it in let us understand it for finite dimensional vector space. It is, you can do it actually uh, for any like yeah, so for any any vector space, but just for understanding, let us assume that V is a finite dimension, and then I'll ask you what would be the infinite dimensional analog of it. So let us first understand this result, assuming that V is finite dimension. Okay, so let V be a finite dimension vector space. Okay, over F, and W is some vector space over. Okay, and assume that we have a basis, since it's finite dimension, V is finite dimension, so assume that this is a basis of V. Now then, I know from the previous observation that if I know what happens to these basis vectors, I can know what happens to an arbitrary vector. So this idea I will use in stating this result. So if suppose we have fixed a basis, let's say v1 to vn for V, then if I choose n arbitrary vectors, any arbitrary vectors, okay, n arbitrary vectors in W, let's say W1 to Wn, W, let's say subset of W, then you can say that there exists a unique linear transformation from V to W such that T of Vi is equal to Wi. Okay. Now this result, what it says that if you have a basis for V, then you just have to choose n vectors in W, any arbitrary vectors of your choice. They can be same also, this W1 to Wn, they can be same also. You just have to choose n vectors such that you can send these Vi's to Wi. That is the idea. So what this result says that once you have fixed a basis for V, then you choose any n vectors in W, and then you can find a unique linear transformation, let's say T from V to W, such that T of Vi is equal to Wi. Okay, so linear transformation T from V to W such that T of Vi equal to W. Now this gives you a way to define linear transformation. So if I fix a basis, then one of you can give me a different set of Wi's, and based on that I can define my linear transformation such that Vi goes to Wi, or some other of you can give me a different set of vectors, and depending on using this result I can define another linear transformation that sends Vi to Wi, and so on. So basically this gives you way to define linear transformation. Okay, this result is not difficult to prove, so we'll prove it in the next class. Okay, so we can stop here. So before I close today's session, let me ask, is our speed is fine? I mean, it seems like we are going very slow, or should I like speed up little bit?
No, sir, it's okay.
It's okay,
It's okay, sir.
because we are not covering much.
It's
Yes,
fine,
sir.
sir.
It's fine. Okay, all right, then we can stop here. You try to practice on Gradescope, try uploading your responses and see if there is any difficulty in doing that. Okay, we can stop here now. Thank you.
Sir, after
Thank you, sir.
minors, you can speed up little bit.
After minor exam?
Sir, after minors, you can speed up before that. Please.
Okay. Yeah, I can do it.
Sir,
The only thing, yes.
sir minor कब से है?
So there is the dates are mentioned in the institute
19
calendar.
September. 19 September.
Yeah, so yeah, let me tell you that before minor we will have a quiz. So I'll fix a date for that. So we'll have a quiz before minor, one quiz at least before minor exam. Then we'll have minor exam, and then after minor and before major exam, we'll have two more quizzes. So there are, as I mentioned earlier, there will be three quizzes, one minor exam and one major exam. So the first quiz would be before minor, I'll fix some date and then communicate to you.
Okay, sir.
All right.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
धन्यवाद.
Thank you, sir.
Thank you.
Yeah, you're welcome.